Hey everyone, this is the quiz review for quiz 5, last one. I'm going to try and kind of move through this quickly so that it'll upload to YouTube more fastly. So let's go ahead and get started. First thing you'll see is this table. This is something you haven't been given before. You're going to get a question. I'll point it out when it comes up. It'll be pretty obvious. That's going to show you a bunch of really complicated molecules, and you're going to have to calculate the enthalpies that are present in all the bonds in them. And you'll just be given a chart that looks like this, and it'll help you figure out what's on, what's in each of those bonds. So it's not something you have to memorize. It's going to be given to you. Okay. So first one says, choose the selection which correctly identifies the forces which must be overcome to convert HOOH from a liquid to a gas. So they're showing you this compound, and they're asking you what forces are present in this. Well, for starters, you know London dispersion has to be there because everything has London dispersion. Second, you would look for hydrogen bonding. Hydrogen bonding is when you have a hydrogen, like so, bonded to an oxygen, a nitrogen, or a fluorine. It's got to be directly bonded to one of those things. If it's like an H bonded to like a C, and then there's also a fluorine in that same molecule but not directly bonded to the H, then that's not H bonding. So the H has to be directly bonded to N, O, or F. Then a nice trick with H bonding is that whenever you see that, it tells you that you also have dipole-dipole, which is the third force. So these are your three options, and HOOH would have all of them because everything has London, it has hydrogen bonding, and the presence of hydrogen bonding also tells you that you have dipole-dipole. So usually what I do when I get this question is I just kind of hope that I'm going to get something with H bonding, and then that'll tell me that I have everything. But that's not always the case. For example, you could be given this pH3, and if you draw the Lewis structure out, you get this guy. So this would have London dispersion, LD. It would not have hydrogen bonding because P is not nitrogen, oxygen, or fluorine, but it would have dipole-dipole, DD, because if you look at this geometry, 4 domains with one of them being a lone pair, that gives you trigonal pyramidal, which is a polar shape. So this is considered polar. So this would be an example of something that just had the 2 of those. All right, but anyways, the question wanted us to see HOOH, which had all 3. So I would go with answer E on this worksheet: London dispersion, dipole-dipole, and hydrogen bonding. Okay, so the next, they ask you to sort the following in order of increasing boiling point. So they want you to do HE, AR, and BF3. And for very complicated reasons that I'll talk about later, when something is heavy, that means that it has a higher boiling point. So all you're really going to do for this question is just sort them from lightest to heaviest. So you'll look up the masses off the table and then just lightest to heaviest. That's all you got to do. So I'm just going to tell you HE weighs 4, AR weighs 40, and BF3 weighs 67. Okay. So that tells me that this is the order they should be in, with BF3 having the highest melting point, AR in the middle, and HE first, because lightest to heaviest. So I would go with answer B. Okay. Then next, we've got this one. So they will show you a picture that looks like this with gas at the top, liquid here, so gas, liquid, solid. And they'll just point to each one of the arrows and they'll state which phase change is happening at that arrow. So, you know, you should just know that like a solid to a gas is sublimation, or like a gas to a liquid is condensation. Like you should just know the basic phase changes. This is not a difficult thing to just look up if you don't know what they are right now. So I'm just going to tell you arrow 3, which shows a solid to a gas, that's sublimation. So I would go with A as the right answer because that is indeed what it shows. And then B is freezing, C, melting, D, vaporization, and E, condensation. And then if that leaves anything out, you know, just look it up or just figure it out for yourself. I mean, freezing, like you can figure it out. It's not hard. Okay. The next, he says, so it's this next one is going to be the same idea, but instead of using a chart, he's just going to put it in sentence form. So he says that ice cubes removed from a freezer slowly turn to liquid water if allowed to warm up. What is the correct name of the phase transition represented by this process? So you have ice cubes, which are solid, going to water, which is a liquid, and obviously that is melting. I would be extremely disappointed in you if you didn't know that. Okay. So next is this question, this awful question. So it says they want you to choose the statement from the following multiple choices that deal with aspects of vapor pressure and intermolecular forces that is false. So they want you to find the false statement. Sometimes they'll ask you to find the true statement, so, you know, just be aware. So they're showing me mostly true things here, and I'm looking for the one that's false. Sometimes it's the other way. So first, they say that CCl4 is more volatile than CBr4. So the difference here is that you have chlorine versus bromine, and bromine is heavy. Bromine is like twice as heavy as chlorine is. So that means that bromine, CBr4, is the heavy one, CCl4 is the light one. So if something is heavy, that means that it has strong intermolecular forces. So like London dispersion, like you know all those forces we talked about in the first question. So, or actually, I'll write this on a new sheet. So if something is heavy, oh my god, this is embarrassing. If something is heavy, that means it has strong intermolecular forces. So the forces that compress things and try to turn them into a solid, those are strong in things that are heavy. And if something has strong intermolecular forces, it has weak vapor pressure, VP. So intermolecular forces tell things to compress and become a solid. Vapor pressure tells things to do the opposite. If something is a high vapor pressure, it wants to expand and turn into a gas. So intermolecular forces and vapor pressure are kind of antagonistic to each other. Something that gives something strong intermolecular forces weakens its vapor pressure, and vice versa. So another thing to realize is that vapor pressure is the same thing as volatility. Technically they mean two different things, but anything that increases vapor pressure increases volatility. So just think of them as the same thing. So once again, we said that CBr4 is heavy. CCl4 is not as heavy. So if something is heavy, like CBr4, that means it has strong intermolecular forces, weak vapor pressure, which means weak volatility. So this statement sounds pretty true. CBr4 should be the one with less volatility than CCl4 because CCl4 is lighter. Okay, and remember, we're looking for the false statement here. So then B says that liquids have lower vapor pressures at higher temperatures than they do at lower temperatures. Okay, so essentially, so whenever you see something is at low vapor pressure, something like that, that means they're saying something is not very likely to turn into a gas under whatever conditions they describe. So if they say high temperatures, that means they're saying liquids have a small chance to turn into gases, or they're less likely to turn into gases at high temperatures. And just from reality, you know that that's not true. If something is hot and you keep heating it up, it's going to turn into a gas at some point. So they're saying that temperature doesn't make things turn into a gas, or that heating things up doesn't make them more likely to boil or turn into a gas or whatever. So clearly you know that that's not true. If you heat something up, it turns into a gas. So that has to be our answer, because that is clearly false. And then I feel like I'll go ahead and go through the rest of these just to give you a good idea. So C says that water boils at lower temperatures at high altitudes than it does at low altitudes. So if you go to high altitudes, like on top of a mountain, then up there's less atmosphere. That's why they say it's hard to breathe on top of mountains. So if there's less atmosphere, that means that there's less atmospheric pressure. And that means that there's less stuff trying to do this to you. At sea level, we're exposed to the full weight of Earth's atmosphere trying to compress us. And if you go on top of a mountain, there's not as much atmosphere to do that. So that means that it's easier for things to do that, to expand. So vapor pressure has an easier time on top of mountains. So in general, things have higher vapor pressure on top of mountains. And if something has high vapor pressure, meaning it's easy for it to turn into a gas, then that sounds about right. Water boils at lower temperatures on high altitudes, because if it's easier for things to turn into a gas at high altitude, I wouldn't need to heat it up as much to make it boil. So yeah, C sounds pretty true to me. D says that substances with strong intermolecular forces have low vapor pressure. Yeah, that's just fundamentally true. Strong intermolecular forces mean weak vapor pressure. And then E, the average kinetic energy of boiling water molecules is lower on a mountaintop than it is at sea level. Yeah, because if water is boiling at lower temperatures at high altitudes, then obviously it's not going to have the same amount of kinetic energy. It's going to have less. If something's really, really hot, it's going to have high kinetic energy. If it's not as hot, it's going to have less kinetic energy. So E sounds pretty true as well. Okay, then the next one deals with this graph here. So hopefully you can see that. So what it shows you is three phases: a solid phase, and I'll switch to a nice colorful pen, a solid phase, a liquid phase, a gas phase, and then there's 4 points you should be aware of. There's the critical point up here, there's the normal boiling point here, there's the normal melting point right here, and then there's the triple point here. And so it would be a good idea to understand that at the normal boiling point, that's when liquid becomes gas at normal pressure. So they call it normal boiling point. So if they ask you about that, you should understand that this is the point where it's transitioning from liquid to gas. So that means that if they ask you what phase it's in and they give you the coordinates of the normal boiling point, you should say both. You should say it's liquid and gas. Same with the normal melting point, except solid and liquid, because it's transitioning between those two. And then the triple point is where it exists as all three phases at once. So at that exact pressure and temperature, it's solid, liquid, and gas all at the same time. Okay, so then you just kind of have to answer questions about this graph, and then if you know all those points and all those phases, then you should be pretty solid. So first they say at temperature 239.82 and pressure 1 atmosphere, this thing exists as part solid and part liquid. So at 239 and pressure 1 atmosphere, so they're giving you the coordinates of the normal boiling point here. They say it should exist as part solid and part liquid. No, that doesn't really make any sense. There shouldn't be any solid involved at the boiling point. It should be liquid and gas. So A, rule that out. Then B, at temperature 195.5, so right around here, and pressure 1 atmosphere, NH3 exists only in the liquid phase. No, that's the melting point. So I know it's not exactly the melting point, 195.49 and 195.5, but that's the melting point. So you would say that no, it's not just liquid. It really is part solid and part liquid. So B, I would rule that out. Okay, then C, at 217.66 degrees Kelvin and pressure 1 atmosphere, this thing exists at just at the gas phase. So at this temperature, which we don't really have on this graph, but you know that it falls somewhere between 195 and 239, so somewhere in here, and then pressure 1 atmosphere, so somewhere along this dotted line, they're saying that it should exist only in the gas phase, which no, this is the liquid phase up here. So I would say that should be the liquid phase, not the gas phase. So C is wrong. And then if you get to D, 195.5 degrees Kelvin and pressure 1 atmosphere is called the normal melting point. Yeah, 195.5, pressure 1 atmosphere, that is the normal melting point indeed. So I would go with D. Okay. Next is this question, which is also terrible. So they're going to show you two compounds, and they're going to put them in an order, and they're going to give you a reason for putting them in that order. And the order that they put them in is from higher boiling point to lower boiling, or higher melting point to lower melting point. So they're saying KBr is a higher boiling point, has a higher melting point than BR2 because of blah 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 reason. So what you have to do is make sure that the order they put these two things in is correct. Then you have to make sure that the rationale that they give for that order is also correct. And this question really sucks because there's just a lot. There's just so many different reasons and things that they can come at you with, and really it draws back from a very long time ago in this course. Lattice energy can be a genuine thing that they ask you about, and you would actually have to be able to do the lattice energy and interpret the meaning of it. So I would honestly say this is the question that I can help you the least on. There's just a lot you have to know for this. So I'll go through it and I'll give you all the advice I can. But for this question, I'm really going to have to say that the best thing you can do is just practice this one a bunch. You have unlimited attempts on practice 5 for this question, so I would just go practice the hell out of it if I was you. But anyways, so first they say that KBr has a higher melting point than BR2 due to the higher molar mass of BR2. So if something has a higher molar mass, that makes it heavier, obviously. And if something's heavier, then that means that it has stronger intermolecular forces. And if something has strong intermolecular forces, that means that it would require a lot of energy to make it get closer to a gas. So if Br2 is truly the one that's heavier, then it would require a higher melting point to convert Br2 into a liquid. But they say that KBr, which is lighter, has the higher melting point, which that just doesn't make sense. The heavier thing should ideally have the higher melting point because its forces are stronger and it requires more energy to overcome those forces. So A is wrong. Okay, then Si greater than SiF4 due to covalent network bonding in Si versus dispersion forces in SiF4. So this is something that you'll want to be aware of. There's something called a covalent network solid. And if you get that in this question, it makes it a lot easier. So forget, that's not a covalent. I just had that written off to the side. So these are 4 that you should be aware of: diamond, graphite, SiO2, and Si. So if you see one of these things, then that means that it's a covalent network solid, and it should always have the highest melting point. That's how those things work. If you see a covalent network solid, then it always wins the melting point contest. So diamond, graphite, SiO2, so those should always have a higher melting point. And the reason should talk about covalent network bonding in blah versus whatever other forces in the other thing. So here they say Si, which is a covalent network solid, greater than SiF4 due to network bonding in Si. So that sounds pretty good to me. So I would go with B. And, like if they give you diamond, they're going to say diamond. You don't have to know like a formula or something for diamond, So just know those 4 things. I think there might be like 1 or 2 others that WebAssign can throw in there, but just know that anytime you see something higher than something else due to covalent network bonding, I would go with that. Okay, and then before I move on from that one, I just want to give you this one example because these 2 examples because this is pretty important for you. So if they show you something like this, this is one that I've seen a number of times, aluminum versus H2O. So if you compare these 2 things, their weights are pretty similar. H2O is 18 and aluminum is like 26 or so. So like they're pretty close. They're not really far enough apart that you would say aluminum is way heavier, so it's got to have the higher melting point. They're not that far apart. And then you would also realize that H2O has hydrogen bonding and dipole-dipole forces, which aluminum doesn't have either of those. It just has London dispersion. So, you would think, all right, H2O is going to be the one that's higher, but for some reason, there's just this kind of concept that we didn't really talk about, which is, I think this is how WebAssign phrases it, metallic character, or metallic bonding. And so in this particular example, you would want to understand that metallic bonding, as it were, is a stronger form of bond than H2O. So in this case, you would say, yeah, that order makes sense because of metallic bonding. That's not really something that we spend a lot of time talking about, but just be aware that's one that's weird and that's out there. Another thing they could ask you would be something like NaCl versus, let's do KCl. So if we compare these 2, their weights aren't that different. They're only different by like 10 or 15 mass units. It's not that big of a difference. So weight isn't really the factor that makes one have a higher melting point than another. So what you would have to look at then is lattice energy. So if I do because lattice energy has a pretty considerable effect on melting points. So if you remember doing lattice energy, the first thing you do is you multiply the charges of the two things that are in the compound, and you take the absolute value. So the charge of sodium is +1 because it's in the first column, and the charge of chlorine is -1 because it's in the second to last column. So 1 times -1, absolute value is 1. Same thing with KCl, 1 and -1, so absolute value is 1. Okay, the thing that has the higher charges multiplied is the thing that has higher lattice energy. But we have a tie here, so that means that we have to do it based on row numbers. So you'll look up the row number of Na, which is on, so Na is over here, it's on row 3, row 1, row 2, row 3. K is on row 4, and Cl is over here on row 3. So if I add up the rows that all those things are on, so Na on row 3, Cl on row 3, they add up to 6, and K on row 4 and Cl on row 3, this adds up to 7. So for charges, and again, I realize I'm just recapping lattice energy for you. I know you already know how to do this, I hope, but it's important, so I'm going back through it again. So normally when you do charges, whatever has the highest charge, that'll be the thing that has the highest lattice energy. But if you get a tie, you do it with distance like this. And then when you do the sum of the rows, the thing that has the higher sum is the thing that has the lower lattice energy. So that means that we would say 6 is less than 7, so NaCl is the one with higher lattice energy. So I would say this order makes sense. NaCl is a higher melting point than KCl, and the reason being that because these two things are closer together to each other on the periodic table, that means that the distance between ions is less. That's the definition of what it is. And the equation, like the actual formula for lattice energy, involves distance between ions. That's what you're figuring out when you're summing up the rows like that. The closer two ions are together, like within an actual bond, then the harder they are to separate. So that gives it a higher lattice energy. So this is the actual reasoning, and this would be the correct order. So yeah, that's all I'll say for this question. I think really you should just keep practicing it, until you've seen all these crazy tricks that it has. I would say these are two ones in particular that are kind of really annoying and tricky, but once you know those and you know all the weird things that it can do, I think you'll find this question easy enough, but you just have to practice it. Okay, so next, this question is another one that you guys mostly haven't seen. So it says to choose the answer which presents the formulas blah 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 in order of increasing solubility with these substances in water. So the way this will go is they will either give you organic formulas or inorganic formulas, and the two have very different rules for how you govern their solubility. So if you get something that's organic, examples of that include things that look like this. For example, like just big crazy molecules with all these C's and H's and O's, things that you have really never seen before. Those are organic compounds. Inorganic compounds are things like KCl, NaCl, PO4, 3 minus, like just things you've seen all semester long. Just they shouldn't look weird to you. Organic things should look very weird to you. Okay, so if you get organic things, then in water, the most soluble thing will be whatever has the most OH groups. So if something has 2 OHs, like this thing I drew up here, then that would probably be something that's pretty soluble. Then, if there is a tie, the second thing you look for is whatever has the least number of carbons. So like this 6 right here is telling me that this compound has 6 carbons in it. If there was something that had 5 carbons in it, that would be more soluble than something that had 6. So first, look for whatever has the most OHs. If there's a tie, then look for something that has less carbons. That's all you do. The other thing to notice is that they will either give you water as the solvent, or they will give you something called hexane as the solvent. So the only difference between water and hexane is that this order will flip for hexane. So water and hexane have opposite orders to each other. So my recommendation is that you just find an order for water. So just do it this way, regardless of what it says on the paper, just do it for water. And then if you see that the solvent is hexane, then just take whatever order you had and just flip it backwards, and then that's your answer. So just do it, always do it for water, flip it backwards if you see that it says hexane. Okay, so organic things I think are honestly easier. So then, next, for inorganic things, what you'll want to do in water is you'll look for things that are ionic. So something that's ionic would be more soluble than something that wasn't ionic. Next, you'd look for things that had hydrogen bonding, so an H bonded to N, O, or F. Then you'd look for things that were polar, so something that's polar is more soluble in water than something that is non-polar. So I would say that's the order to go with. And then again, if it says hexane, then it's just the opposite. So flip it around. So do it for water. If it says hexane, take your order and just flip it around. Okay, so in the question that we actually have, they want you to do pH3, NH3, and NH4Cl. So I would say that NH4Cl, that's ionic, because remember that NH4 is the exception to the metal non-metal thing. So NH4Cl is ionic. So that would tell me that NH4Cl is the most soluble. Then NH3 has hydrogen bonding, so I would put that next. And then pH3 is just polar. That's all it has going for it. So that would be the least soluble. So I would take that as my order for water. And then just to show you what I mean when I say flip it around, if I was talking about hexane, I would say this, NH4Cl, NH3, pH3. Okay? So we want the one that goes like that. A, pH3, NH3, NH4Cl, most soluble. Okay. So the next is the limiting reactant one. So for this guy, they give you some equation, which is kind of hard to read, so I'll write it out. It says 4NH3 plus 5O2, it gives you 4NO plus 6H2O. Okay, so next they tell you some mass of NH3. So they say you have 8.62 grams of NH3. Then they also tell you that you have 4.62 grams of O2. So this is just a standard limiting reactant problem. You did this for quiz 1. You've probably done it on various different homeworks. Like, this one shouldn't be super weird to you, but you should remember that anytime you get a limiting reactant problem, the first thing you always do is turn your reactants into moles. So I'm going to divide each of these by their molar masses. So the molar mass of NH3 is just 17. The molar mass of O2 is 32. So when I divide both of those, that tells me that I get 0.615 moles of NH3 and 0.144 moles of O2. So next, I need to figure out which of those is my limiting reactant. So to do that, I divide the moles by the coefficient that goes with each one. So my moles of NH3, I'm going to divide by 4, because that's the coefficient for NH3 from the equation. My moles of O2, I'm going to divide by 5, because that's the coefficient that goes with O2. And when I divide those things, we get 0.154 for NH3, and we get 0.0288 for O2. Whichever one comes out lower is your limiting reactant. So I know that O2 is the limiting reactant. Then, to find the product, it's very simple. So in the question they tell you they want to know how much H2O forms. So we're looking for H2O. So you simply take the limiting reactant times whatever the coefficient is that goes with the product. So we're looking for H2O, so the coefficient of H2O is 6, times, because they want it in grams, times the molar mass of the product. So the molar mass of H2O is 18. So when I multiply all that stuff out, I get 3.11 grams of H2O, which looks a lot like answer C to me. Okay, so then moving on, next one. So this one is a net ionic equation question. So solubility rules will come up again for this. But the gist is he's going to tell you you have two things reacting with each other. So this is just what he tells you you're reacting from the problem, this thing and this other thing. And he's going to ask you, what do you get out when you react these two things? So what you do is you take the first thing and you put it with the last thing, and you take the second thing and you put it with the next thing. So you're kind of like foiling it, more or less. So Ba goes with PO4, and Na goes with NO3. Okay, so next, the way this will always work, one of these products is going to be soluble and one of them is going to be insoluble according to the solubility rules, which he should give you. If he gave it to you for quiz 2, he's going to give it to you for this. So I remember from the solubility rules that NO3 makes everything soluble. So that tells me that NaNO3 is the soluble one. And because you'll always have one soluble product and one insoluble product, that means that if NaNO3 is soluble, BaPO4 must be insoluble. So that means it gets a little parentheses S to denote that it forms a solid. The S stands for solid. So anything that doesn't form a solid, though, means that it must be insoluble. So that means we can just dissolve everything. So rewrite this as Ba plus NO3 plus Na plus PO4 going to BaPO4 solid, doesn't break up because it forms a solid, and then Na plus NO3. So we've got all these ions here, and they make this one singular solid. So anything that isn't part of this reaction, we're going to get rid of it. So if something doesn't change from the left side to the right side, we're just going to remove it. So Ba becomes a whole new thing, so I'm going to keep Ba, but NO3 just comes out as NO3 at the end, so I don't need that. So scratch that out. Same thing with Na, it just becomes Na again, so I don't need it. Okay, so then rewrite this as Ba plus PO4 going to BaPO4 solid. Okay, now you're almost done. You just have to make sure that this is balanced. So start by putting charges in. So the charge of Ba is +2 because it's in the second column. PO4 is a polyatomic ion. Hopefully you remember those. So you would know that PO4 has a -3 charge. Then to find out how they come together here, swip, swap, soda pop. The charges become the subscripts for the other things. So that means that this 3 goes there, and this 2 goes here. So whenever you're doing an ionic compound and you want to see how two things come together, that's what you do, swip, swap, soda pop. Okay, so now this whole thing has been put together, but it's not balanced because I have 3 Bas on the right, I only have 1 Ba over here. Same with PO4, they're not the same. So you have to balance it. So we just say coefficient 3 there, coefficient 2 there. So 3 Ba plus 2 PO4 minus 3 going to Ba 3 PO4 2 solid. I would say that is your answer. And that looks like E to me. Okay. So next, the question that we need the big chart for . So he will show you some reaction. I drew it out again because it's kind of hard to read on this paper. He'll show you some reaction with like the structures for things all drawn out. And he'll ask you, what is the net enthalpy change in this reaction? So to do this, what you need to do is pull up the chart, and then with this chart, we're going to tally up one giant number for the reactant side and one giant number for the product side. And then we'll take the difference between them, and then that's what we need. So for the reactants, we've got this big molecule here. So I notice that I have 1, 2, 3, 4, 5, 6, 7, 8 carbon to hydrogen bonds. 8 carbon to hydrogen. Then I've got 1, 2, 3 carbon to carbon bonds. And then I've got 1, 2 carbon to oxygen bonds. And then I've got 1, 2 hydrogen to oxygen bonds. Okay, then I'll do the same thing for the product side. So this thing and this thing are my products. So again, starting with H to C, I've got 1, 2, 3, 4, 5, 6. So 6 H to C bonds, or C to H bonds. Then I've got 1, 2, 3 C to C bonds. And then I've got 1, 2 C to O double bonds. And then I've got 2 H to H single bonds. Anytime there's a coefficient like that, it means you have 2 of this entire thing. So any bonds that are in this parentheses, you have double. Okay, so I have 1 H to H here, but there's a coefficient, so that means I have 2 H to H bonds. All right, so now I'm going to tally up 2 big numbers. So C to H is 413. So we're going to say 8 times 413. Then C to C is 348. So we're going to say 3 times 348. Then C to O is 358. Then H to O is 463. Okay. Then for the products, H to C was 413, so 6 times 413. And then carbon to carbon, we said was 348, so 3 times 348. Then C to O double bond, so that is down here, 799. C to O is 799, so 2 times 799. And then we have H to H last, so H to H, where are you at? 436. So 2 times 436. And when you do that, you should find that the product side comes out to 5992, and the reactant side comes out to, when you add these things up, the reactant side comes out to 5990. And what you do is you take reactants minus products. Okay, so we're going to say 5990 minus 5992, and that should give you -2. Okay, so it's reactants minus products, right? This is very easy to confuse. I confuse this. I feel like I've probably told someone already like the wrong order for this. Like it's very easy to confuse. So don't forget that it's reactants minus products. Okay. So the answer you should get for that one should be E, -2, E. Okay, so then next one that we got is this physicsy one down here. So it says, what is the energy output of a light source in joules per second if it produces 511 photons per second? And these photons have a wavelength of blah, then they give you the speed of light, and they give you h. Okay, so the equation that you need for this is E equals hc over lambda. So we're just going to plug in. So this E is the energy of a photon, a single photon. H is 6.63 times 10 to the minus 34. They tell you that. C is 2.998 times 10 to the 8. And lambda is 121 nanometers, except remember that anytime you put nanometers into an equation, you're supposed to say times 10 to the minus 9, because it has to be in meters, so that's the conversion. So if I plug all this stuff into the calculator, you can't really see that, 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 121 times 10 to the minus 9. That gives me that E is equal to 1.64 times 10 to the minus 18. So the energy of a single photon is 1.64 times 10 to the minus 18. But what the problem asks you is, what is the energy output of this light source per second? And they tell you that it makes 511 of these photons per second. So if you want the energy output per second, you're going to say this times 511, or whatever the photons per second are. And when you do that, you say 1.64 times 10 to the minus 18 times 511, I get 8.39 times 10 to the minus 16 joules per second. So that looks like, to me, answer E, 8.39 times 10 to the minus 16. Okay, so next is quantum numbers. So this is a very easy question. You just have to remember the rules for quantum numbers. They're just going to give you a set of numbers, and you just have to remember what they are. So n just has to be a whole number. Nothing's ever going to be wrong because of n. L has to be between 0 and whatever n was minus 1. So L has to be between 0 and n less than 1. Then ML has to be between negative L and positive L. And then the last one, MS, just has to say plus a half or minus a half. Doesn't matter which one it says. So if we go by those rules, then n equals 5. That's cool. Then L, so if n is 5, L has to be between 0 to n minus 1. So L would have to be between 0 and 4. So it is, so that's cool. Then ML, it has to be negative L to positive L, so negative 1, 0, or 1 would be the options here, and it is one of those, so that's fine. And then MS is plus a half, which MS just has to say plus a half or minus a half, doesn't matter which one. So I would say A sounds pretty good. All right, then the next one, this is the big resonance structure one where you have to pick the best structure. So they want you to draw N2O. You did this on like quiz 3, I think. So they want you to do N2O, and they specifically tell you to write out the Lewis structure in this order: N, N, O. And you should remember when we did this for quiz 3, there's always going to be 3 possibilities. No matter what structure you're given, they will look like this. And you just fill this in. So N, N, O, N, N, O, N, N, O. And then just go back and put in however many pairs of electrons they need to have 4 total. So like I'm giving this one 3 because it already has 1. Giving this one 2 because it's already got 2, just needs to get to 4. Okay, so now we have our 3 structures, and we need to figure out which one of these structures is the best. That's what they want you to do with this question. So to find the best one, you assess the formal charges that are present here. So the formal charge is a comparison between how many electrons something has and how many electrons something wants to have. So nitrogen wants to have 5, and in this case, because nitrogen has 5 valence electrons, so because it's in the 5th column, so it wants 5. So this nitrogen has 1, 2, 3, 4, 5. So this nitrogen has exactly as many as it wants. So we say that it is neutral. Its formal charge is 0. So again, nitrogen wants to have 5 because it's supposed to have 5 valence electrons because it's in the 5th column. So this nitrogen here has 1, 2, 3, 4. So it's missing an electron. So if you're missing an electron, that makes you positive by 1. So then O in the 6th column has 6 valence electrons. So it wants to have 6, and it's got 1, 2, 3, 4, 5, 6, 7. So it has 1 more than it needs. So that makes it -1. If you have an excess of electrons, you're negative. Okay? So then, moving on, this one, so nitrogen wants 5. It's got 1, 2, 3, 4, 5, 6. So that makes it -1. Nitrogen, same deal as above. It's got 4. It's always going to be +1 for that middle row because they all have 4. So then O wants 6, and it's got 1, 2, 3, 4, 5, 6. So it's neutral. All right. So then this bottom one, start with N. N wants to have 5, and it's got 1, 2, 3, 4, 5, 6, 7. So that means it has 2 more than it wants to have. Nitrogen has 5 valence electrons. Here it has 7. So 2 more than you want makes you -2. And you never want to have a charge bigger than 1. So like these two things are fine. This is way too big though. This is more than 1 charge on a single thing, which is considered wrong. So anytime you see a charge bigger than 1, just scratch that structure out. All right, so now we're deciding between these two, and this is something that people always have a hard time with, but whenever you get a situation like this where you have 2 structures that have exactly the same amount of charge on them, they both just have 2 1 charges. So whenever you get 2 structures with the same charge, there's going to be a difference in where those charges are placed. So the only difference between this top one is that the -1 is over O. And in this bottom one, the -1 is over N. So you have to, based on electronegativity, decide which one wants the -1 more. So you should remember that electronegativity is how much something wants to have a negative charge. If something is really electronegative, it wants to be negative. So electronegativity is based on how close something is to fluorine. The closer to fluorine, the more electronegative. Oxygen, if you look at the table, oxygen is more electronegative than nitrogen is. So that means oxygen wants a negative more than nitrogen does. So we settle for this one. Okay? And if this had been a positive charge instead of a negative charge, it would have been the opposite. If something really wants to have a negative charge because it's really electronegative, then it's definitely not going to want a positive charge. So if it had been a positive charge, yeah, I would have given it to this one. Okay? So then the actual answer choice, you just compare your chosen structure to various things that they mention in the choices. So they say that the leftmost bond is a double bond. Nah, that's a triple bond. The rightmost bond is a triple bond. No, that's a single bond. The formal charge in the leftmost N atom is -2. No, that's never going to happen. The number of non-bonding lone pairs of electrons on the leftmost N atom is 3. No, this only has this has 1 lone pair. Then the number of non-bonding lone pairs of electrons on the rightmost atom is 3. So 1, 2, 3 pairs. Yeah, that sounds about right to me. So I would go with E. Okay, and then the last one, easy one. So they just want you to draw this structure, SO3 2-. So we're drawing this, and then they want you to state what the electron and molecular geometry are. So do the Lewis structure. Count up your valence electrons. S and O are both in the 6th column, which means that they both have 6 valence electrons. So 6 plus 6 plus 6 plus 6. So that tells me that I have 24 total. Then I'm going to add 2 because this compound has a -2 charge, which means I'm giving it 2 extra electrons. Then I'm going to subtract 2 for every bond that I put in place. So -6 leaves me with 20. And I need to make sure that all the outside atoms have their octets fulfilled. So we're going to give 18 away in total, 6 to each oxygen. And that leaves me with just 2 remaining. And then I notice that S only has 3 pairs, so that means it conveniently needs another pair of electrons. So I'm just going to take those 2 and I'm going to give them to this S. Okay? So then you have to, in order to determine the geometries, you have to count up the number of domains that this has. So this is 1, 2, 3, 4 domains. And it's not relevant here, but remember that double bonds and triple bonds, those are also just one domain. Like a triple bond is not 3 domains, it's just 1. But anyways, this compound has 1, 2, 3, 4. So that tells me that its electron domain geometry is a tetrahedral. So we are tetrahedral, and then the molecular domain geometry is a tetrahedral with 1 lone pair. So if I look at my handy chart here, I just had this waiting this whole time just for this one question. A tetrahedral with 1 lone pair gives me trigonal pyramidal. So that means my molecular geometry is trigonal pyramidal. So I'm going to pick the answer that says EDG tetrahedral, MDG trigonal pyramidal, which must be B, tetrahedral, trigonal pyramidal. Coolio, everybody. And then it wouldn't be a Sully video if I didn't show you the setup here. Okay, so we got a pack of staples, some dumbbells, and then a much bigger sword this time. Look at that guy. I got that from this weeb, I know. So, you know, anyways, good luck on quiz, what is this, 5, everybody. And then after that, I'll see you for the final. So, keep it cool, everybody.